Greetings. In this video, I want to start to teach you how to calculate a refrigeration cycle. The problem is not how to solve a single problem, but once you learn how to calculate a refrigeration cycle, then you would be able to calculate different problems with different configurations or different knowns and unknowns. But before I start the specific problem or a specific calculation, I have to teach you some background on how refrigeration cycles work. Well, assume that we have a heat reservoir, which is this one. It is a high temperature reservoir, so we would call it TH. And there's a cold temperature reservoir, which is TL. These are two reservoirs which we have here. Now, we all know, we have learned from the second law of thermodynamics that if we use this temperature difference, we could extract work. The natural way of heat transfer between these two reservoirs is from hot reservoir to cold reservoir. But how could we transfer energy from the lower temperature reservoir to higher temperature reservoir? That's a very important industrial question. And how they do it is that they use the basic key process that helps us with it is throttling. And how they achieve it. Assume that you produce a colder environment here, okay, and call this point 1. This is colder environment than TL, so there would be heat transfer from TL to this environment. Then you compress this medium, whatever there is, to a warmer temperature and to a higher pressure. You do work to it, and then you would have your medium at a warmer temperature than your hot environment and your high temperature reservoir. So if you put them in thermal contact, then temperature would be transferred from this medium, this high temperature medium, into the high temperature reservoir. This would be point 3. So your medium has cooled down due to heat transfer to high temperature reservoir. And finally, the key process is the throttling process. You have a cold medium, and your cold medium has high pressure. You expand it. This is expansion to a point 4 to a lower temperature, and this expansion produces low temperature. And as I mentioned, it's the temperature lower than your low temperature reservoir. So the cycle would go on, heat would be transferred from low temperature reservoir to the high temperature reservoir. Basically, this cycle facilitates the heat transfer from a cold temperature reservoir to a high temperature reservoir. So this process is called compression. This problem is just the heat transfer and is done in an evaporator, they call it. And this process is done in a condenser. And the expansion could take place in two different instruments. It could be, and usually is, in a throttling valve, or in, if our medium is a gas, it could be done in a turbine. Both uh, are used quite often. It's in a throttling valve, but sometimes it is in a turbine. So what we have now is a refrigeration cycle. This cycle works, and our low temperature reservoir could be inside the refrigerator, and high temperature reservoir could be inside the kitchen. Heat pumps also work on the same cycle. If you have a heat pump, then the low temperature reservoir could be the cold temperature outside, and high temperature reservoir could be the room temperature. And this cycle would transfer. Basically, it would absorb heat from the cold temperature reservoir, we would call it QL, and would deliver heat to high temperature reservoir, call it QH. In a Rankine cycle, as we know it from the study of the second law, these two temperatures are equal, and there is ideal reversible heat transfer here. Also, these two temperatures are equal, and there is ideal reversible heat transfer here. This one is an ideal compressor, and this one is ideal expansion, which assumably it happens in a turbine. But in a real refrigeration cycle, there is a temperature difference here, and our medium is colder than our low temperature medium. There is a temperature difference here, and our medium temperature is higher than the high temperature reservoir that we have. So this QH and this QL could happen in practice. Now, once we know how this idea works, then we would see how in practice they produce it. Now, assume that we have a TS diagram, and the medium that we usually is usually used these days is R134A. Previously, R12 or R22 were used. Ammonia is still used in occasions, but R134A is very common for our daily daily refrigeration problems. So, if this is the uh, if this is the medium that we use, now how we would use this medium inside this cycle, or how do we apply uh, such a cycle to this medium? And the way we do it is that the compression needs to take place in single phase. So either it has to be a liquid that is compressed, or it has to be vapor that is compressed. So what we do is that we take a point like 1, and compress the medium to a point like 2. Ideally, uh, in many books, it is said that ideally it is done uh, in an isentropic manner. But if some heat is lost, then although that lost heat is part of the work that is done, but still the work that we need for um, isothermal process is less than the work that we need for an isentropic process. So sometimes it's better if point 2 is in fact somewhere at a lower entropy than point 1, or sometimes if the compressor is isentropic, then you would have point 2 where some entropy is generated due to irreversibilities. But for the time being, let's assume that our compressor is ideal and it is isentropic. That's the assumption in many problems. But then this point 2, which is here, it has a higher pressure and high temperature. So it comes into contact with our high temperature reservoir and cools down sometimes up to here and sometimes even to a lower temperature, which would be here. Let's call this point 3. If it cools down to point 3, or call this point 4 if it cools down to even a lesser temperature, and you would have some compressed liquid. Then there is the throttling process. The throttling process brings it is irreversible. There is no doubt that it is irreversible, and it would be point 5, where point 5 would enter this process. In fact, just to comply it with this one, I would call this point 4. You see, our green markings are green color is what is really happens. It is 3 or 4, and this is 5, as it is drawn here. And then it comes to a point 6, and then it might be heated somehow to point 1, just to make sure that anything that enters our compressor is vapor and there are no liquid droplets in the compressor, so that there would be no damage to the compressor. So there is sometimes a heat exchanger where we cool down what is out of the point 3 to point 4 and use it to heat what is in point 6. The evaporator exits to a warmer temperature like point 1, so that whatever that enters the compressor is a vapor, is a superheat vapor, and we are sure that there are no droplets here. R134A droplets here, and there will be no damage to the compressor. What I do now is to draw both the ideal cycle and the real cycle here for you so that you would know the difference. The basic cycle for this cycle that I have drawn is usually like this. There is a condenser. This is a condenser. There is an evaporator. This is an evaporator. There is a compressor. This is the compressor. And the outcome goes to the condenser. We do work in the compressor. This would be point 1. This would be point 2, just like this one here. Here would be point 3. There is an expansion valve, which is point 4. And then it is expansion 5, and the point 4 would be here. And the cycle just goes on. The cycle just repeats. And just this system does the refrigeration. In fact, this system, this cycle, does just what we just explained in this one here. Now, if there is a heat exchanger here, then the cycle would change. I mean, what happens is that this is the free body diagram of it. This is the condenser. This is the condenser. This is the evaporator. Evaporator, which are the basic items of this cycle, since this one has the duty to extract heat from a colder reservoir, and this one has the duty to deliver heat to a warmer reservoir. Now, what happens is that whatever that goes from the evaporator goes out of the evaporator, which is here is point 6. First goes to a heat exchanger. Let's put a heat exchanger here. Goes to a heat exchanger and collects some heat. Then it goes to a compressor. And then it goes to the condenser. So this would be point 6, this would be point 1, and this would be point 2, just like what I have put here. And also, after the condenser at point 3, initially the fluid would go to the heat exchanger, would provide the heat that this evaporator exit medium requires, this one from 3, and then it is 4, and then it goes to the throttling valve, and then it goes to 6. So, in fact, the process that I have drawn here for you, the diagram that I have drawn here for you, is the green diagram. I would just redraw the lines with green just to show that the green diagram just thus includes that heat exchanger, which collects heat from the condenser exit and delivers heat to the evaporator exit, and the rest of the cycle is just as before. So this is our cycle. This is a simple cycle, just like what we had discussed here. And this is one further complication to the cycle, where there is a heat exchanger added to the cycle, and The job it does is that it ensures that the medium that enters the compressor is in fact superheat. It collects the saturated vapor from the evaporator exit, heats it just a few degrees, and then lets it into the compressor inlet. Now let's put some numbers to this refrigeration cycle. And what they usually do is that we work on two different pressures, which on saturated lines, they have, of course, uh, some corresponding temperatures. Now, it's often said that they define evaporator temperature or pressure, but as far as condenser is concerned, they call it pressure because they usually know this. It's often known that the condenser entry is a superheat uh, medium, is superheat R134A, and therefore condenser does not have a constant temperature, but evaporator usually has constant temperature. Now, the problem I want to solve now is between two different pressures where for evaporator, the pressure is 200 kilopascal. 200 kilopascal is the evaporator pressure, and its saturation temperature is minus 10.09. 10.09 degrees C is its saturation temperature, or 200 kilopascal. As far as the condenser is concerned, the pressure is 900 kilopascal, and we know that its saturation temperature is 35.51 degrees centigrade. So here we know the, in fact, limiting pressures for both condenser and evaporator. Now, the other knowledge that we know is that here we assume that the entrance to the throttling valve is 5.51 degrees C, less than 35.51. So, in fact, the temperature at point 4, T4, is 30 degrees C. It is selected such that the uh, such that the temperature would be easily readable from the table. Now, the other knowledge that we are given is that at point 6, which is the evaporator exit, it is saturated vapor. Point 6 is saturated vapor, but as I mentioned, just to make sure that no liquid droplets would enter the compressor, it's good to heat it just a few degrees. We don't know how much heat is added. And the compressor, for the time being, we assume it to be isentropic. I've selected this problem from the book by Singel, but I have changed it. I have just selected the numbers, and I would do far more than what it is required from that problem, and I also am using a table from the same book. This is the table for R134A, and the point with this table, this is the table for R134A, and in this table we have both information for saturated R134A at 200 kilopascal, and also a few lines down we have all the knowledge for 900 kilopascal. And what I do here is just to uh, read those values, from that table and copy them here, whatever I need. What I need is are the two pressures, evaporator pressure and condenser pressure, their saturation temperatures, and also for refrigeration problems, what we need is HF, HFG, HG, and SF, SFG, and SG. We need all these values here, which basically what I have copied here are all the information for this point, okay, this point, and this point. So these are all the knowledge that I have copied on that table. So we have this point. I just put it with a cross, this point. This is HF, HG for 900 kilopascals, and this is HF and HG for 200 kilopascals. And these are all properties of R1348. They have nothing to do with our problem. The point is that they are just relevant with our problem because the problem happens on these two lines. But there is no need to calculate them because they are properties of 134A, and they are the same whatever our problem should be. So once we have these knowledge, now it is enough for us to calculate the rest of the points in this cycle, all other points of the cycle, and see how we could use those points to calculate cycle properties. Well, it's a good practice to just draw a table and put all the properties of our different points on this table. Our points are 1 to 6, and I just try to see whichever knowledge we have from for these points from our tables, from whatever we already know, and there are some properties that we need to calculate, and therefore we do so. Now, just to start with the problem, the easiest way is to look at it from points 6 and 3. These are the 2 points that are very, very easy to read because this one is saturated vapor and point 3 is saturated liquid, and we have all their knowledge from the table above. So a lot of the pressures are also known because all our pressures are on the 2 constant pressure lines. Say point 1, we know that it is 200 kilopascals. Point 2, we know that it is 900 kilopascals. Point 3 is 900 kilopascals. Point 4 is once again 900 kilopascals, and point 5 and point 6 are both 200 kilopascals. So we have this knowledge For point 3, we know that it's saturated liquid, so its temperature would be 35.51. Point 4, we just calculated it. It's 30 degrees C. The problem has told us what its temperature is. And for point 6, it is minus 10.09. It is saturated vapor. And for point 5, all the same, it is minus 10.09. Point 5 has some quality, but still, this temperature is a function of its pressure. And since its pressure is 200 kilopascal, then its temperature would be minus 10.09. For point 6, while you are at it, we have all the knowledge is at 200 kilopascal, and its Hg and Sg are its values. So H is 244.46 and S is 0.93773. These are the values that I have just read from this table. There is no problem with that. Now, as for the point 3, for point 3, still HF, it's on 900 kilopascals. HF and SF are its properties. So for point 3, I could put down 101.61 and S is 0.37377. So as for point 3, we have all the knowledge. For point 4, it's easy to read all values from saturated liquid at 30 degrees. You remember that at compressed liquid part, the changes in pressure do not change properties that much. Changes in temperature are far more important, and we could read all properties from saturated liquid from the same temperature. So for point 4, we just read values from the table at 30 degrees C, and for H, it is 93.58, and SF is 0.34789. And these are the values that we may have for different points, at least just simply from the table. The rest of the values we need to calculate from different processes and from the configuration, which I would just do it in our next video. Thanks for watching this one, and I will calculate and solve the rest of the problem in the next video. Cheers.